In the previous section, we showed that subatomic particles, like electrons, will exhibit wave-like properties under certain situations. If electrons are fired at a double slit, for example, they form an interference pattern of bright and dark fringes on a screen behind the slits. The bright fringes correspond to the regions where there is a higher probability for the electron to strike the screen. Since there are a number of bright fringes, there is more than one place where each electron has some probability of hitting. As a result, it is not possible to specify in advance exactly where on the screen any individual electron will hit. All we can do is speak of the probability that the electron may end up in a number of different places. No longer is it possible to say, as Newton's laws would suggest, that a single electron, fired through a double slit, will travel directly forward in a straight line and strike the screen. This simple model just does not apply when a particle as small as an electron passes through a pair of closely spaced narrow slits. Because the wave nature of particles is important in such circumstances, we lose the ability to predict with 100% certainty the path that a single particle will follow. Instead, only the average behavior of a large number of particles is predictable, and the behavior of any individual particle is uncertain. To see how this uncertainty arises, let's consider the simpler case of passing electrons through a single slit. When we pass light through a single slit, as in section 27.5, a diffraction pattern is observed with a bright and wide central fringe. A similar pattern is observed when electrons are used. The central fringe is bright because electrons strike the screen over the entire region between the first dark fringe, both above and below the central bright fringe. Let's just consider the electrons that form the central bright fringe. In this case, any individual electron could strike the screen anywhere between the first dark fringe above and the first dark fringe below the central fringe. The extent to which these electrons are diffracted is given by the angle theta in the drawing. In order to reach the locations within the central bright fringe that are not directly across from the single slit, some of the electrons must have acquired momentum in the y direction, despite the fact that they enter the slit traveling only in the x direction and have no momentum in the y direction to start with. The figure illustrates that the y component of the momentum may be as large as delta py. Thus, delta py represents the uncertainty in the y component of the momentum in the sense that the y component may have any value from 0 to delta py. Recall from our study of single-slit diffraction with light that the angle that locates the first dark fringe is given by the following. Now we assume that lambda represents the de Broglie wavelength of the electrons. If the angle theta is small, then sine theta is approximately equal to tangent theta. Moreover, the figure indicates that tangent theta is equal to delta py over px, where px is the x component of the momentum of the electron. Therefore, delta py over px is approximately equal to lambda over w. We write px as h over lambda, and we find that delta py is approximately equal to h over w. This indicates that a smaller slit width w leads to a larger uncertainty in the y component of the electron's momentum. In other words, the smaller we make the width of the slit, the more accurately we know the position of the electron, but the uncertainty in the electron's momentum grows accordingly. It was Heisenberg who first suggested that the uncertainty, delta py, in the y component of the momentum is related to the uncertainty in the y position of the electron as the electron passes through the slit. Let's put y equals 0 at the center of the slit. We know each electron must pass somewhere through the slit, which in this case would mean that its vertical position in the slit would be between plus or minus w over 2. This represents the uncertainty in the vertical position of the electron. Substituting this result into the expression above gives the following. This indicates that the product of the uncertainty of an electron's momentum times the uncertainty in its position must be on the order of h, Planck's constant. Heisenberg's more complete analysis showed that the following is true. This is Heisenberg's uncertainty principle for momentum and position. It places limits on the accuracy with which the momentum and position of a particle can be specified simultaneously. These limits are not just limits due to faulty measuring techniques. They are fundamental limits imposed by nature, and there is no way to circumvent them. Heisenberg's uncertainty principle states that delta py and delta y cannot both be made arbitrarily small at the same time. If one is small, then the other must be large, so that their product equals or exceeds Planck's constant divided by 4 pi. For example, if the position of a particle is known exactly, so that delta y is 0, then delta py would be an infinitely large number, and the momentum of the particle would be completely uncertain. Conversely, if we assume that delta py is 0, then delta y is an infinitely large number, and the position of the particle would be completely uncertain. In other words, the Heisenberg uncertainty principle states that it is not possible to specify precisely both the momentum and position of a particle at the same time. There is also an uncertainty principle that deals with energy and time. The product of the uncertainty delta E in the energy of a particle and the time interval delta t during which the particle remains in a given energy state is greater than or equal to Planck's constant divided by 4 pi. Therefore, the shorter the lifetime of a particle in a given state, the greater is the uncertainty in the energy of that state. The uncertainty principle has significant consequences for the motion of subatomic particles, but has little effect on macroscopic objects.